everyone, welcome to Algorithm Seminar. Today we're happy to have Marika here to give a talk. She's a rising fifth-year PhD student at Boston University, advised by Adam Smith. Her research spans differential privacy, cryptography, and their intersection with legal questions. And more recently, she has become interested in practical implementations of differential privacy. Before interning at Google, she was a visiting assistant professor at Reed College. She has also done research for two-mode labs. Please welcome our speaker.
Right. Thank you. So I'm excited to tell you about this work on differentially private sampling from distributions. This is joint work with Sofia Raskolnikova, Sachin Sivakumar, and Adam Smith. All right, so let me just start by giving you some context and private data analysis. So we're imagining that we have a data set where each row contains data from an individual. All this data is sent to some central curator, and later, some data analysts want to learn information about the data set. And so in this area, there's kind of a fundamental question, which is what information about the data set that doesn't heavily depend on individual entries can the curator compute efficiently? And so the curator has two conflicting goals. They want to, protect the privacy of individuals. Maybe this is a very sensitive data set, for example, while at the same time providing accurate information because it's also probably quite useful data. So this area has been very well studied, and there's a rigorous and mathematically informed notion called differential privacy that captures this idea. So we'll say two data sets are neighbors if they differ in one individual's data. So in this example, we can change x3 to anything that we want. And we'll say that an algorithm is differentially private if its output is roughly the same for all pairs of neighbors. And so just looking at the output, you can't determine whether x or x prime was used. Okay, so it's a condition on the algorithm itself. And so more formally, we'll say an algorithm is epsilon delta differentially private if for all pairs of neighbors and all possible sets of outputs, these two things are close. So in particular, the probability that the algorithm has an output in this set S only differs by an e to the epsilon factor, multiplicative factor in the two cases, and a delta additive factor. So epsilon and delta kind of parameterize how much privacy you're losing by doing the computation. And so a larger epsilon and delta means that you're losing more privacy, and a smaller epsilon and delta gives you higher privacy. And like for typical values, you can think of epsilon being like close to 1, depending on like what circles you're in, and delta being small, like less than 1 over n, like 1 in a million or something. All right, so differential privacy is this great notion that has lots of useful properties that we can use to analyze algorithms. So one is composition, right? So if you have two algorithms that are each epsilon 0 differentially private, then their composition, running both of them on the same data set, gives you 2 epsilon differential privacy. It also satisfies group privacy. So if A is differentially private, then it protects not just individuals, but groups. So changing a group of k individuals' data gives you a k times epsilon difference in the output distributions. And this property is actually key to the proof that I'm going to present. So that's kind of the most important one in this list. But also differential privacy satisfies post-processing. So basically, if your output or if your algorithm is differentially private, then any kind of post-processing that you do to it can't increase the privacy loss as long as that post-processing is not dependent on X itself. And all these properties hold for epsilon delta differential privacy with some variation in the parameters. Okay, I should also say, like, you can just interrupt me with questions. I don't know, I probably won't really see the chat if anyone posts things, so just like maybe someone can let me know if there's a question, or you can just interrupt. All right. So now that we've kind of oriented ourselves to differential privacy, let me introduce the problem that we actually study called private sampling. This was a new problem from this paper that we wrote. And so basically, the algorithm gets n records that are sampled IID from some unknown distribution, but from a class that's known to the algorithm. And its goal is to privately generate a single sample from a distribution that's close to the original one. Okay. And I should say that the output distribution of the algorithm gets randomness both from the selection of the data set and the coins of the algorithm. And so we want to do all of this using differential privacy. And we'll imagine that like each input record corresponds to one person's data. So in contrast to like other like typical learning goals where you have to produce a whole description of Q that's like accurate, here we're just trying to generate a single sample. Okay, so when I say that P is close to Q, what do I mean? So we are defining accuracy in terms of total variation distance. So we'll say a sampling algorithm is alpha accurate on a class of distributions if for all distributions in that class, the total variation distance between P and the algorithm's output distribution is at most alpha. And the algorithm gets to know what the class of distributions is, and this kind of represents like it encodes any information or assumptions that the algorithm gets to make about the class of distributions. And we wanted to formulate this as kind of the weakest sort of, I don't know, weakest non-trivial learning goal, and kind of see what we could prove about it in the private setting. Are there any questions before I continue? Okay. So let me give you a little bit of context in this problem. One thing to note is that if you're in a non-private setting, meaning you don't care about differential privacy, this is trivial to do. You only need one IID input sample to generate one IID output that's according to the same distribution. So you can get a perfect sampler with one input sample. But with privacy, it's actually surprisingly hard because we can't just output one of the input samples. Another thing to note is that privately learning a distribution implies that you can also privately sample from it. So if we're given a description of Q, we can also generate a sample from Q, or really like any number of samples. And so lower bounds on private sampling are also lower bounds on private learning. And while this task is like, maybe not super like realistic, there are some applications where generating some plausible data might be enough, and you might not want to have to learn the whole distribution. So for example, if you're writing unit tests for algorithms that are running sensitive data, and you don't want to like have to waste a bunch of privacy budget learning the distribution of your input. All right. So in this work, we formulate this new problem of private sampling. We give.
You have a question from Molly.
Oh,
Yes, sorry,
yeah.
just wanted to ask. So, will you generate only one sample, and there is like an additional privacy cost to generate multiple samples, or how does it work? If you're interested in getting many samples.
Yeah, that's a good question. So in this work, we just consider generating one sample. You could generate like a constant number of samples with just using like a larger data set, but we don't yet know how to like generate multiple samples. Yeah.
Okay, thanks.
Yeah, so we study the sample complexity of this problem. So how many input samples you need to generate a single output sample. And we study this for several classes of distributions and give tight bounds on those. And then we relate the sample complexity to like the complexity of private learning and non-private learning. So interestingly, what we find is that for some parameter settings, the complexity of private sampling is just as hard as the complexity of private learning. When in other settings, private sampling is actually much easier than private learning. And for some distribution classes that we study, we find that the complexity of private learning is equal to the complexity of private sampling plus the complexity of non-private learning. And so to the extent that private learning is harder than non-private learning, for these classes, you can account for that difference by the complexity of private sampling, although we don't have like any formal connection among these tasks besides just the sample complexity. All right, so we were originally inspired by this Axelrod et al. Paper that considers an analogous problem in the non-private setting, where they're trying to generate MIID observations when given a sample of size only n. And I believe they call this sample amplification. And this work is also related to distributed sampling, where each player gets one observation and is limited in their communication. We compare our bounds to the bounds for private and non-private learning tasks. And we also use some techniques similar to sampling from Bayesian posterior distributions to get some privacy for free. So we do use sampling to improve the privacy, but our techniques are a bit different. This is also, of course, related to generating synthetic data that has characteristics that you want. And more recently, quite recently this summer, actually, there's been immediate follow-up work on sampling from Gaussian distributions and products of Bernoulli's by some folks at Google and I think University of Waterloo. All right. So let me give you an overview of our bounds. So I've made this table with our DP sampling bounds from this work, and also the non-private learning bounds and the private learning bounds from prior works, so you can kind of see how they compare. We start by looking at kind of the simplest distribution class, which is just Bernoulli distributions, and find that we need 1 over alpha epsilon samples, where alpha is the accuracy. Then we generalize this in 2 ways. First, we consider expanding to distributions on k items, and we find that all the bounds scale with k. And we also generalize to products of Bernoulli distributions and find that generally the bounds scale with d, as expected. And then we study this kind of interesting subclass, products of Bernoullis, where the bias on the Bernoulli is bounded by 1/3 and 2/3. And this is the regime where learning is the hardest, but we actually find that you can privately sample from these types of distributions with roughly square root of d input samples. So it's actually like easier even than non-private learning. Okay, and you'll note here that like for Bernoullis and distributions on k items that we have this pattern that the complexity of private learning is equal to the complexity of non-private learning plus complexity of private sampling. So it'd be interesting to study this phenomenon more in detail, perhaps. All right. So we use a number of different techniques in this work. For our upper bounds, we can actually exploit the randomness of sampling to get privacy. And this is because we don't need to, like, we only need to be correct on average. So for example, if you have an unbiased estimate of P, then you would have a perfect sampling algorithm, unlike in learning. And for product distributions, we use this recursive private preconditioning technique from Kamadli, Singhal, and Ullman. And for our lower bounds, typically how a learning lower bound proof might go is you might say, well, in order to learn a distribution, if you can do that, you can identify the distribution from some set of distributions. And then you might argue that differential privacy prevents this if you don't have enough samples. We can't really do that here because a single sample is not enough to identify a distribution. So instead, what we argue in two of our proofs is that sampling implies that that the output will be in the support of P most of the time. And then we argue that if you don't have enough input samples, differential privacy says that you won't be in the support of P to get our contradiction. So the specific details vary by class. For k-ary distributions, we give a custom argument that I'll present here. And for product distributions, we can actually reduce from this k-ary lower bound. And then for products of bounded Bernoullis, we can reduce from estimating one-way marginals. Okay. So here's just like a simple example of an algorithm for sampling from a Bernoulli with bounded bias. So the algorithm gets n draws from this Bernoulli as input and just needs to produce a single bit as output. So what we can do is compute the sample proportion, clip to a slightly smaller interval, 1/4, 3/4, and then return a sample from the resulting Bernoulli. And I claim that this is epsilon 0 differentially private when n is at least 4 over epsilon. And if you're familiar with differential privacy, then this might be surprising because we're not actually adding any like Laplace noise or Gaussian noise. Like it doesn't have the typical structure. And yet like clipping and sampling is enough to get privacy. Oh, was there a question? Yeah.
Yes, just a quick question. Does the privacy proof assume that the input come from Bernoulli, or would the privacy hold even if it's completely arbitrary?
So I believe that the privacy, I would need to check the details, but I think that the privacy proof holds even if the bias is not bounded. But really the accuracy relies on that fact. But I would need to double check. So I don't want to say the wrong thing. I'm not sure.
Okay.
But it requires it to be Bernoulli.
Yeah, it has to be Bernoulli. Yeah.
Binary at least, right?
Yeah. Yeah.
Bernoulli IID, I guess.
Yeah.
Yeah, okay.
I mean, I guess I could imagine just drawing a sample from the Bernoulli with like tilde p as being like the randomness that gives you differential privacy, or like you also require that randomness in x1, x2, x up to xn.
Oh, for the privacy holds for all input data sets.
Okay.
Yeah.
But like,
the-
yeah, okay.
Yeah.
Okay.
Yeah. Yeah, and then this algorithm is also alpha accurate when n is some constant times log 1 over alpha. And so to get both of these, it's efficient to have order 1 over epsilon plus log 1 over alpha input samples. And you can compare this to privately learning from this class where you would need order 1 over alpha epsilon plus 1 over alpha squared inputs. Okay, but that's just like a simple example. I want to get to the main result, which is proving this k-ary lower bound on k items. So let's let C sub k be the class of distributions on 1 through k. The lower bound from this paper says that n, the number of input samples, has to be at least k over alpha epsilon for any private sampler to be alpha accurate. And so I guess the question is like, how do we prove this lower bound? We're just trying to show that outputting a single sample is hard, and it's hard to be accurate. And so we rely on a few observations. Basically, we need to find a subclass of distributions such that privacy will contradict accuracy if you don't have enough inputs. So one kind of key observation is that if you're alpha accurate, and recall that we're measuring accuracy in terms of total variation distance, then the sampler has to output an item that's in the support of the distribution with at least 1 minus alpha probability. That's kind of a minimum requirement. We also argue that for sufficiently small n, every DP sampler must output an element that doesn't appear in its input with some probability. And then we basically choose distributions such that if an item was not in the input, it's unlikely to be in the support of the distribution. And so these 3 points will lead to a contradiction and lead us to conclude that n has to be at least k over alpha epsilon. Okay, so for this talk, I'm actually going to prove a simpler lemma with some assumptions. I've chosen this just to avoid all the headaches of dealing with all these parameters. But I think it still shows the core of the argument, and you'll still get a sense for like why this lower bound holds. And then if there's time, I can talk about how to remove the assumptions, but we may run out of time. Okay, so we're gonna prove this theorem in spirit so assuming that the sampler's epsilon 0 differentially private rather than epsilon delta. We're gonna assume that it's frequency count based, which I'll explain in a few slides. And we'll prove it for fixed accuracy. So it'll be 1 over C accurate for some constant C. And we'll assume that the data set has a size that's distributed as Poisson of n. So the bound that we're aiming for is to show that n has to be at least k over epsilon. So we've removed the dependence on alpha, but this is like the analogous bound that you would get. Okay, and I have made a little box with the assumptions. The formatting got a little weird, but hopefully that will give you a reminder what we're assuming. All right, so the hard class of distributions that we're going to consider are ones that are uniform on k out of 2k elements. So it's uniform on half of the space. Okay, so let me explain what frequency count based is. It makes our analysis a lot easier. Right, so given a data set and some integer j, we'll say that fj of x is the number of elements that occur j times in x. And f of x will be the frequency counts. So as an example, let's say our universe is the integers 1 through 24, and we have this data set that I've just sorted for ease of reading. Then the frequency counts for this data set are as follows. So for example, there are 19 things that appear 0 times. There are 3 things that appear once, right? So 1, 5, and 18. 1 thing that appears twice, and so on. And so a sampler is, we'll say it's frequency count based if for every element in the universe, the probability that the sampler outputs that element depends only on j, the number of times it occurs, and the rest of the frequency vector. So in other words, the labels on the items don't matter. The output doesn't depend on the specific labels. So we could output a 1 and a 5 and an 18 with equal probability. And so in our paper, we prove that, for our class of hard distributions, if you can sample from this with like a private sampler that's alpha accurate, then you can also sample from it using a frequency count based sampler. And we're relying on the fact that this class of hard distributions is uniform, so it doesn't really matter what the labels were to begin with. So we can assume this without loss of generality, right? So we're not incurring any additional terms in the accuracy or privacy parameters. All right, so that's not really a strong assumption, but it just makes things a lot easier to analyze. All right, so let me kind of show you how we're going to prove this lower bound, or like the steps to getting there, and then we'll start actually diving into it. So we're first going to prove that for a fixed data set, sampled from some fixed distribution in our hard class of distributions, that the probability of returning an item with 0 count is lower bounded by this quantity that depends on, the counts of the other items and epsilon. Then we're going to prove that in expectation over data sets, that this summation in the denominator is order k, if n is smaller than k over epsilon. And then together we can put these together to prove our simplified lower bound. So if you're accurate, then the probability that you return something not in the support is at most 1 over c, and there are k things not in the support, so k times this expectation of p0 will show is lower bounded by a constant. Okay. So let's start by proving proposition 1. Right. So so first notice that if we sum up the number of items that occur j times the probability of releasing something that occurs j times, that gives us just the probability of releasing really anything in the domain. So that's 1. We can then separate out the terms for releasing something with a count of 0, right? So just kind of separating out that first term. And then using a key lemma that I'll show you in a minute, we can relate the probability of releasing an item that occurs j times to the probability of releasing an item that occurs 0 times. And this is by like a group privacy argument in differential privacy. And then the rest is pretty much done for us. So we can just factor out this P0 term and notice that F0, the number of things that occur 0 times, will be at most 2k because the universe size is 2k. So we can upper bound it by 2k. And then just dividing both sides by 2k plus that summation gives us the result that we want. So up to like this, the proof of this key lemma, are there any questions on how this works so far? Okay. Yeah, so this key lemma is really what's doing the heavy lifting in the lower bound. So let me show you what that is and how it works. Okay, so our key lemma says that for every differentially private sampler and every data set and every frequency count, that the probability of releasing an item that occurs j times is at most e to the epsilon j times the probability of releasing something that occurs 0 times. So really, like, you can't release something with non-zero count that much more than with a 0 count by privacy. Okay, so let's fix some data set and a fingerprint and an index and fix a sampler. And let's let this notation x sub a to b denote a data set that you get by taking x and replacing every instance of some element a with some other element b. So for example, if this is our original x on the left, and we replace every 5 with a 6, we'll get the result on the right. Okay, so let's take any element that occurs j times in x, and let b be some element that does not occur in x. All right, so by group privacy, we know that replacing j occurrences or j people's entries will give us a factor of e to the epsilon j in terms of like the probability of releasing that item. So the probability of releasing item A in the left data set is at most e to the epsilon j times the probability of releasing A when there's no A in the data set anymore.
Mhm.
Okay, so notice that the fingerprint stays the same. So we haven't changed any of the counts, just the labels of the counts. And since A is frequency count based, we know that these two probabilities will be equal then. Doesn't care about the labels. And so what that tells us, because on the right side, A doesn't occur at all, so the probability that the algorithm releases A is actually tells us how likely it is to release a 0 count item. And so we get the desired result in the end. So this is pretty much where the whole lower bound comes from, and nothing more. Just the rest. I mean, there's of course other details, but this is really what gives us the lower bound. Okay. So going back to what we previously proved, if we with this key lemma in mind, we've just replaced this p sub j with e to the epsilon j times p0. So that's kind of the only thing that that's really happening in this proof. Okay. All right, so we've going back to our overview, we have proved this first proposition. Now let's look at the second result that we need. So now we're not working with a fixed data set, but instead we're looking at the expectation over data sets. And Okay, so I'm not going to give a full proof because the details aren't like super interesting, but I'll give you like the main points. So if we let n sub I be the number of times element I occurs in the sample, then it turns out that we can relate the quantity in the summation with like e to the n sub I. So if you're counting the number of items that occur j times and summing over j, that's just equal to e to the n sub I epsilon, where we're summing over all of the items in the data set. Okay, and by our assumption, we said that the data set size is distributed as a Poisson, and each of the inputs are drawn independently. So n sub I is also distributed as a Poisson, Poisson of n over k. And so you can just use the moment generating function of the Poisson distribution to get the following bound when epsilon is less than 1 and when n is smaller than k over epsilon. Okay.
Wait, where did you assume that Ni is Poisson? Or that the total number of elements is Poisson?
Oh yeah, if you look in the top,
Oh, okay.
yeah, I guess I should have listed it in the proposition as well. But yeah, the assumption that the input data set size is Poisson.
There's an expectation. Expectation n.
Oh yeah.
I see.
Good. Thank you.
And this is all just for like the simplified version of the lemma, but like the actual statement from the paper has these things like
Yeah.
afterwards. Yeah.
Yeah, the actual proof of the full theorem has all of these key ideas, but just like more
Yeah.
parameters and hassle. Yeah. Okay. Yeah, so we've like sort of proved proposition 2. And now let's like put all of the pieces together. Okay, so let's let Q sub AP denote this output distribution of A when it's given draws from P. By 1 over C accuracy, since we're measuring it in terms of total variation distance, we know that the total variation distance is at most 1 over C between the output distribution and the given distribution. And that quantity is at most the probability that we don't output something in the support. And so that's equal to, there's k things that are not in the support of the distribution. And so we just take k times, the probability or the expectation of the probability of returning something not in the support, like an individual item. Or sorry, an item with 0 count. Okay, so right, so by proposition 1 and Jensen's inequality, if we take the probability now over x, not for fixed x, on proposition 1, we get this k over 2k plus the expectation of this summation. And then okay, so this is what we have so far, just kind of taking out all the intermediate terms. And then by proposition 2, if n is less than k over epsilon, we said that the expectation is scales like k. So we get k over 2k plus order k, which gives us a lower bound, a constant lower bound. And so if you take C to be large enough, meaning the accuracy is good enough, we get a contradiction to the fact that n is less than k over epsilon. Yeah, so are there any questions on how we kind of put all these things together?
Your lemma relied on the group privacy guarantee. That's unique to like epsilon 0. Does it break when you go to epsilon delta or other intermediate notions?
Yeah, good question. So I have a slide on that. I don't know, but basically there's a similar group privacy result for epsilon delta DP. I'll show it to you in a minute. But it just introduces more terms that are a little bit annoying to deal with.
Sure.
So so let's talk about how to remove the assumptions. So one thing we assumed was that the data set size is distributed as Poisson of n. And in the paper, we prove that you can remove this assumption just incurring a small additive term on the accuracy, where like higher accuracy is worse. So if there's a DP sampler that's alpha accurate on a class where the data set size is fixed to n, then there's also a DP sampler that's slightly less accurate on data sets of size distributed as Poisson of 2n. So to remove this assumption, we incur like a small additive factor, but it's not so bad. And then to remove the assumption that delta is 0, so we want to prove for epsilon delta DP samplers, we use this key lemma, which is analogous to the one that we saw, except there's this extra delta over epsilon term. And so this changes the analysis a little bit. So the remaining argument works basically in the same way, as long as delta is less than k over 10 alpha epsilon. And then you can do some like privacy amplification to get delta up to 1 over 5,000 n. Yeah, so but the key ideas behind the argument still work. Okay, and then by far the hardest assumption to remove is the fixed accuracy. So to get a dependence on alpha, you have to use a different class of hard distributions. So this is the one that we use. Basically, it's again like uniform over k out of 2k elements, but then there's this special element, the last 2k plus 1, that has a large probability mass. And so the k elements that we were looking at before will have mass 50 alpha. So in order to be accurate, you still have to like output things from there most of the time. So that complicates the argument a bit more, which is why I decided to leave it out for this talk. Yeah, does that answer your question?
Oh, yeah.
Yeah, cool. All right, so this is the lower bound that we get in the end. Yeah, I think that's mainly all that I had. Wrapping up, in this work, we formulate this new problem of private sampling, or it was new at the time. And we give tight bounds on the sample complexity for several classes of distributions, and then relate this sample complexity to that of private learning and non-private learning. And there's lots of open problems in this area. So the follow-up work that came out this summer answered some of our questions about Gaussian distributions and sampling from those, but there are still others to consider. And also this question of like how to generate multiple samples, not just a constant number, but more than that. How do you do that without affecting accuracy or privacy too much? Yeah, but that's all I had. Thanks for listening, and I'm happy to take more questions.